In this class, we will look at combining the effect of rotation as well as translation into a single matrix. And we will also see how to the effect of the order of rotations and various angle representations, rotation representations, like Euler representation, roll pitch angle, etc. And so these are going to be useful later on in our forward as well as inverse kinematics issues. Now coming to translation, suppose pure translation, meaning suppose there is a frame, it is translated, its origin is translated to position 1, and we'll call that the distance d1 0. It's a vector expressed with reference to frame 0, and it has no rotation. So any point in this frame can be simply given, can be mapped into this frame 0 by adding the components of this distance of the origin expressed in frame 0. That is what we do here. P0 is P1 plus D10, and P0 components in frame 0 will be whatever are the components in frame 1 plus the XYZ components of this D10. On the other hand, if this frame were to be rotated and then you have got a coordinate P1, you want to express that in frame 0, well, all you need to do is, like we have seen earlier in the earlier lesson, convert that into a parallel frame, a frame parallel to 0 frame by multiplying with a rotation matrix that relates frame 1 and frame 0, rather rotated frame and unrotated frame. And then you get then coordinates in the frame parallel to 0, like the previous case. So all you have is you have R10 P1 in the place of P1. That's all. So this is going to be the new relation if it is taking into consideration rotation also. So there is rotation and also translation. This is the equation. This is for rotation by movement by one frame. Well, we would like to incorporate both effects into a single matrix. We have a rotation matrix, this part R10 here, and this position D10 is incorporated as the fourth column. But then for compatibility sake, what we do is we add one more dummy column, dummy row at the bottom, and also add one more row to each of these position vectors. We augment them as 4 by 1 vectors, so that you have here a 4 by 4 matrix, which we call homogeneous transformation matrix. And we represent now P0 is equal to H10 into P1. Now H10 is a 4 by 4 matrix. That's unlike the previous one. It incorporates rotation as well as position displacement. Okay. Next to the same thing, we'll see in some different detail. Same thing, P0 is equal to distance plus R10 P1. Suppose this frame is further moved to another position by a distance D1 and then further rotated, represented by R21 matrix. Then we have P1 is equal to D1 plus R21 times P2, just like this. Now it's a relation between frames 1 and 2. Now to convert into frame 0, just substitute P1 in this equation. You will get D plus R10, rather R10 D1 plus R10 into R21 P2. If you move to another third frame, then you know this you'll have one more. The equation will have 3 rotation matrices multiplied, etc. Instead of all these linear terms, you can have a single matrix to represent each of these conversions, each of these changes, H10, H21. We have 4 by 4 homogeneous transformation matrices, so that you can look at multiplying each of those matrices, 4 by 4 matrices, to obtain the composition of displacement and rotation. This is what we'll be leading because we try to fix frames on each of the links and progressively right up to the end effector. So we need to relate each frame to the previous frame by a single matrix. That is the effort we are going through now. Homogeneous transformation matrix is one such. Now, coming back to if there is a homogeneous transformation matrix giving only translation and no rotation, then we have this kind of unit matrix in the place of rotation, and the displacement is given by this. And if you want to represent one more transformation between frames 1 to 2 with the displacement d1 or whatever, then the h20 that is relating frame 2 to 0 will be h10 into h21. Okay, then you can go on multiplying this 4 by 4 matrices to give total transformation, and the relation for a point in the last frame to the so-called 0th frame of the base frame. One more simple observation we need to make here is, suppose a homogeneous transformation matrix which has got only pure translation with only along one axis, that is homogeneous transformation matrix with basic translation. Suppose it is along z-axis and it is by d, then we represent HTM like this. Suppose you have rotation without any translation. Translation part will be 0 vector, and rotation will be given by, let us say it is about z-axis by an angle theta. It will be given by this rotation matrix. Now you want to have a composition of these two. You have movement along this and rotation also. Then you can multiply the rotation followed by displacement. It then the nature of this matrix is such, you can simply add the effect of this displacement in this column itself. So you can get rotation as well as translation effect into one single matrix, provided you are doing basic translation and rotation about one axis. This is true in the case if you do it along x-axis, rotate about x-axis and move along x-axis and so on. Okay, now we look at the importance of the order of rotations. Suppose if a frame 0 is first rotated by 30 degrees about z and then about current x-axis. After rotation, whatever is the frame you get, that axis, that current axis, that x-axis, we call the current axis. If you do it by 45, rotate about the x-axis by 45 degrees, then you get the total effect of rotation we get by post multiplying or z theta, z 30 degrees, whatever it is, multiplied by rotation x 45 degrees. On the other hand, if you rotated 45 degrees about x first and then about z by 30 degrees, then same order in which you have rotated will have to be represented here. That is Rx 45 into Rz 30 degrees. That will give the total effective rotation matrix. So also it's important to note that this is not the same thing as this. If you change the order, though you multiplied the same things, but same matrices, but in different order you multiplied, they're not the same because the rotation matrix is not commutative. Okay, so order of rotations is important. Next, one more aspect is what is known as fixed frame rotation. That is, suppose you rotated by z about 30 degrees and then followed with rotation about x-axis by 45, but about x0, original frame, x0, not x1. They are not x1 of the frame that you obtained after rotation by 30 degrees about z. About the original x0 axis if you rotated, then the net rotation is obtained by pre-multiplying. That is, the order gets reversed. That is, first rotation is on the right side, then next rotation about fixed axis will have to be will be a pre-multiplying matrix. So you need to be careful as to what you are doing, to whether you are rotating about a current axis or a fixed axis. If you're rotating about a fixed frame, then the rotation matrices are you pre-multiplied. On the other hand, you post-multiply if you're rotating about the current frames. Then a couple of representations. This is angle axis representation, for example, is one of the examples. That is, you are given one rotation matrix. You have a base frame, base matrix, and then you are given a rotation matrix representing a frame with reference to rotation of a frame with reference to the basic frame. Then you want to you want to represent the new frame as though you obtained it by rotating about some axis and by certain angle. You should be able to get the new rotation matrix or new frame. How to go about that? How do I get that? Well, for that, what you do is you obtain the elements of the rotation matrix, the matrix 1 after rotation, whatever you got. Well, you said you get, it can be shown that theta is equal to cos inverse of the diagonal elements minus 1 by 2. That will give you the rotation angle, and the vector about which this angle, it will have to be rotated by an angle theta, is given by this. That is 1 by 2 sine theta, r32 minus r23, and so on, given by this vector. Well, for example, suppose you got somebody told you, I got a rotation matrix like this. Tell me about what vector I should have rotated by what angle to obtain this from my unit matrix of frame 0. Well, you apply these two equations. Theta will be diagonal elements minus 1 by 2. Cos inverse will be 30 degrees. And the k will be 1 by 2 sine 30 times this vector r32 minus r23. When you do that, you'll get 0, 0, and 0, 0, 1, which is nothing but the z-axis. And rotation is 30 degrees. This is nothing but rz theta, rz 30 degrees. That is what you get, right? Of course, I have taken simple example to demonstrate these two expressions, but it's valid for any arbitrary rotation, arbitrary frame. Next is Euler rotation. Euler rotation is rotation about z by an angle phi, followed by a current frame rotation of theta by an angle about y, and then the current z again. Current z about the current z by an angle psi. Well, if you write the three matrices corresponding to z, y, and z rotations to the respective angles, you will get this matrix in the parametric form. Well, suppose you got a frame matrix, rotation matrix, it's given some numbers. You want to, your question is, if I did the Euler rotation, that is first by z about phi, then the current about the current y by theta, etc. What are those angles? Well, what you do is this parametric form, you compare to those numbers and obtain theta psi phi. For example, theta is already there. The three element is cos theta is equal to some number. So you obtain sin theta as root of 1 minus cos square theta, sin theta cos theta. From that, you will get tan theta, and tan inverse of that, that will give you theta. So from theta, you find phi and then psi. So you can find theta phi psi as though you obtained a new rotation matrix by this Euler type of rotations. Okay, next one. Next one is called roll pitch yaw angles. This is very similar to that, except that these rotations are about z, y, and x in this order, but fixed frame. That is actually you rotate by an angle psi about x, then about the fixed frame about y0, not y1. You rotate by an angle theta, and then about the current about the fixed z0, you rotate by an angle phi. So order is reversed, because fixed frame rotations. When you do that, you get this expression. Similarly, you compare the matrix, that the rotational matrix that you have in numbers to the various elements here, and you can get the theta, phi, psi, and that means you can get that matrix, whatever is given by this kind of roll, pitch, angles, 3 rotations together will produce that matrix. So you can apply roll, pitch, or Euler angles depending upon what you want. But these conversions are going to be uh, useful to us later on when we go to inverse kinematics, and also some of the material we covered about homogeneous transformation matrix will be useful when we go to forward kinematics using Danault-Hartenberg convention and other techniques.